Every major chip maker in 2026 is selling you on the exact same phrase. Local AI. You have seen the slides. 40 tops, 50 tops, even 80 tops jammed directly into ultra-thin laptops. But independent lab benchmarks reveal a dirty secret. Run a local LLM or continuous image generation for just 8 minutes, and that shiny neural processing unit throttles by up to 45%. They promised us full privacy, zero latency, and cloud-free intelligence right on our laps. But when real-world workloads hit the silicon, physics always wins. Today, we break down why NPUs are hitting a thermal wall, why memory bandwidth is choking your system, and whether the AI PC era is actually living up to its promises. To understand what is going wrong, we have to look at how neural processing units work. TOPS stands for Tera Operations Per Second. Microsoft mandated 40 TOPS as the baseline for Copilot Plus certification. Intel, AMD, and Qualcomm rushed to meet and exceed that metric. But TOPS is a peak burst metric, calculated using int8 or lower quantization precision. It tells you how fast the chip can process math in a fraction of a second. Under ideal lab conditions, with unlimited thermal headroom, it says nothing about sustained execution. Unlike CPUs and GPUs, which have established cooling profiles developed over decades, NPUs are designed to occupy minimal die space and share heat pipes with adjacent silicon. When an NPU is pushed with continuous matrix math, heat builds up rapidly. In recent stress tests, machines running 7 billion parameter models continuously hit thermal throttling in under 10 minutes. Token generation speeds plummeted from 25 tokens per second down to 12. That is a 50% loss in responsiveness. So here's my question for you in the comments below. Have you tried running local AI tools on your laptop? Or do you still rely on cloud services like ChatGPT and Claude? Let me know your setup down below. Let us look at how the big chip makers approach this problem. Intel Lunar Lake and Panther Lake designs integrated NPU tiles directly onto the same package with LPDDR5X memory. This cuts latency, but creates a dense heat packet in thin designs. Qualcomm Snapdragon X series uses hexagon NPUs that offer incredible power efficiency for light tasks like background blur and noise removal. But under sustained heavy inference, power consumption scales up, driving up temperatures. AMD XDNA2 architecture faces similar challenges. Here's what makes it worse. Running sustained NPU inference on battery power forces system BIOS limits to kick in unplugged. Power management firmware clamps NPU power targets down by up to 30% to prevent battery drain and thermal runaway. Thermal throttling is not even the only bottleneck. The second wall is memory bandwidth. Local AI models, especially large language models, are memory-bound. Every single token generated requires passing billions of parameters through system RAM into the NPU. Unlike desktop graphics cards with dedicated high-speed VRAM, laptops share system RAM between the CPU, GPU, and NPU. Standard LPDDR5X RAM provides around 100 to 130 gigabytes per second of bandwidth. Compare that to a desktop RTX 4090 with over 1,000 gigabytes per second. Apple tried to solve this with unified memory architectures on M-series Max chips, reaching up to 400 gigabytes per second bandwidth. But on mainstream Windows laptops, unified memory bandwidth remains a major bottleneck that raw NPU tops simply cannot overcome. Furthermore, Copilot Plus PCs shipping with 16 gigabytes of system RAM face immediate limits when Windows reserves 6 to 8 gigabytes for OS operations, and an 8 billion parameter local model takes up 6 gigabyte of RAM. Your system is running completely on the edge. This brings us to our second big question. Do you think 32 gigabytes of RAM should be the absolute minimum requirement for any AI advertised laptop in 2026? Drop a yes or no in the comments right now. Hardware thermal limits are only half the story. Software optimization plays a critical role. Frameworks like ONNX runtime, Intel OpenVINO, and Apple Core ML Determine how efficiently workloads map to NPU execution blocks. Unoptimized software dumps workloads right back onto the power-hungry GPU or CPU. Look at real-world benchmarks. In Stable Diffusion image generation tests, running inference purely on the NPU takes around 22 seconds per image on Lunar Lake, compared to 7 seconds on Snapdragon X Elite. But switch that same generation to the integrated GPU, and generation times drop down to under 10 seconds, at the cost of doubling power draw. This exposes the fundamental trade-off of current NPUs. NPUs are incredible at background efficiency, handling audio noise cancellation, eye contact correction, and light background tasks using fractions of a watt. But they are not mini GPUs. Marketing departments want you to believe that buying a Copilot Plus PC replaces the need for cloud AI infrastructure. Engineering reality shows that local NPUs are designed to handle continuous ambient AI features, not heavy generative workloads that require massive parallel execution and hundreds of gigabytes of bandwidth. So how will hardware makers fix this? Next-generation designs are adopting LPCA MM2 memory modules to increase RAM bandwidth while keeping power consumption low, paired with vapor chamber cooling solutions, even in thin ultrabooks. If you need serious, sustained local AI performance right now, desktop form factors or mini PCs with active cooling remain unbeatable. Desktop GPUs like the RTX 4080 and 5080 series, or workstation Mac Studios provide the thermal envelope and memory bus width that thin laptops simply cannot match. What should you buy today? If you want an ultra-portable laptop for all-day battery life, document summarization, and light productivity, current Copilot Plus PCs are fantastic machines, but do not buy them expecting to run local LLMs or heavy generative AI continuously without hitting thermal walls. If you do want to future-proof your purchase for local AI, prioritize these 3 specs. First, minimum 32 gigabytes of fast LPDDR5X RAM. Second, look for chassis designs with dual fans or vapor chambers. Third, check independent sustained benchmark tests, not peak marketing slides. On-device AI is the future, but hardware physics will not be cheated by clever marketing. If you found this technical breakdown valuable, hit that subscribe button, ring the bell for more real-world hardware deep dive, and check out our videos on this channel. Thanks for watching.